Suppose a car travels along a straight road and with the velocity time graph, which is shown over here. And you can see from here, this is the time velocity graph, velocity on the y-axis and the time on the x-axis. And the graph shows a car which is slowly increasing its velocity, which means it is accelerating at a constant rate until it reaches a speed of 60 kilometers per hour, and it's traveling at this constant speed of 60 kilometers per hour. It then slows down until it is at rest. And so the significance of this part of the graph is that the car is traveling forwards, and the area that we see inside this shaded part is actually the distance traveled by the car. The significance of the second part of this graph is that the car is now traveling in the opposite direction, or we might say it's traveling backwards. And the area represents the distance that it has traveled back. So if we are asked to find the total distance, we would need to add the orange area and the green area together. And we can do that by calculating the area of each section here, dividing them into three: the triangle, the rectangle, and the triangle again. And the same thing in the greens area too. We've got three sections in here. And this will be 12 kilometers plus 4 kilometers. So we end up getting 16 kilometers, the whole distance traveled. On the other hand, if we want to calculate the final displacement, then we're going to need to calculate the distance forward, which is shown by the orange area, and we need to now take away the distance backwards, which is now shown by the green area. So that as the car travels backwards to its original place, we need to take that distance away. That is 12, take away 4, and the final displacement would therefore be 8 kilometers. And from here, I will show you how to find the displacement and the distance, not from the velocity graphs, but from velocity functions using our integral method. So if you subscribe to this channel, you'll be automatically notified when the next video comes out.